and bottom. So now if I ask you to find the slope over here at, we'll say 1/2, or no better number here. What is the slope of the upper half of the circle at 1/2? You plug the number 1/2 into this expression and get out an answer, correct? And it would be negative, right? It's going downwards. But if you plugged in 1/2 over here, right, it's going to be a positive value, right? The slope is positive there in the lower half of the circle. They yield different derivatives, right? But the formulas will work out, right? This will be the negative of that one, and it'll work out fine. So you could do that. So what we want to do is circumvent this whole process of splitting up functions, splitting up relations into different functions, and to avoid that. Not only because it's cumbersome, the other reason is you cannot always do it. You will not be able to write every relation in terms of other functions. They're too complicated sometimes, right? So what we're going to do instead is implicitly differentiate. So implicitly differentiate means assume y is an implicit function of x. Okay? So it's implicit instead of explicit. This is not an explicit function. This is y equals something with x in it. That's called explicit. This is just a relation between x and y. But we're going to assume that y is dependent upon x. And it's implicit because it's not written y equals. Okay? You guys ready for this? Who's seen implicit before? No? Yeah, all right. So when you do implicit differentiation, you're going to take the derivative of both sides of the relation. So we'll start with the expression x squared plus y squared equals 1. And we're going to come to these exact same conclusions that we did over here when we split it up. This will be easier though.
You say you take the derivative of what?
Of both sides of the expression, of the relation. We have a relation here, so it's something equals something. Right? It's not y as a function of anything else. So you got to take the derivative of both sides. But what we have to remember is that y is a function of x. Now, you can't see how it is. You don't know how it is. Right? In any given problem, you don't know how y depends on x. All you know is that it does. That's what you have to assume. Right? All right. So, these problems can become very subtle, especially in the notation. So right now, what derivative, in terms of the Leibniz notation, are we trying to find? D what, d what? What do we want to find here?
dx, dy,
dy over dx. We want to find dy over dx. We could find either one. What we want to find right now is dy dx. Okay? That's the most standard problem, find dy dx, which is the standard slope of the plane, right? dy dx is the standard slope of the plane. All right, so we're trying to find dy dx. So if I'm trying to find dy dx, what derivative operator was applied to y? d dx. So I need to apply d dx to both sides of this, and that could change in some of these problems. Not always d dx, okay? It has been so far for us for the most part, but it could change depending on the subtlety of the problem, okay? So d dx, both sides, what you're doing. You're applying the differential operator d dx to both sides of the relation. X squared plus y squared is going to get that applied to it, and so will the number 1 on the right-hand side. Okay? If two things are equal, if x squared plus y squared is the number 1, then when I apply a derivative to both sides, it should still be equal. All right? All right. The right-hand side is easy. What is it? 0. Right-hand side is 0. Derivative of any constant is 0. You said ddg, ddk, doesn't matter what it is, right? ddd, whatever weird nonsense they give you, it's going to be a 0. So now the left-hand side is the more subtle part. Since you are taking the derivative, this is extremely important. So you're taking the derivative with respect to x, then anything that just has x in it is your standard derivative. When it just has x, standard derivative, right? So this first part, this x squared, is going to go to fabulous. But now we're going to add to it the derivative of y squared. But it is the derivative of y squared with respect to x. If it were with respect to y, it would read 2y. But it's not. It's with respect to another variable down the chain. So y is an implicit function of x. So it's like you have a squaring function, and the function y has been put inside the squaring function. Okay? There's an outer function called the squaring function, and y has been put inside of it. It's another function dependent upon x. So you've got to go through the squaring function and through the y function to get to the derivative with respect to x. So it's a chain rule. So you differentiate around the inner function, right? Take this, the outer function is the square, so you bring the square down. Inner function y stays the same, power goes down to 1, okay? And then how do you finish off the chain rule? You multiply by the derivative of the inner function. So the derivative of y with respect to x now, right? So that's the y prime. And that is the piece you're looking for. So now you have an algebraic equation that you need to solve for y prime.
So if it was inverse, so if it was d over dy, would it be 2x times x prime plus 2y?
Perfect. Yeah, exactly. That's right. And there are going to be questions like that. They're going to switch up the variables on you.
How many variables? Because it could be like
This standard problem could have 3 at most.
3.
Yeah, really, yeah. In these texts with 3.
So you'd have two variables with times in them. So like
That's correct. We'll see some soon. Okay. But right now, you're taking the derivative with respect to a variable that does exist in the relation somewhere, and any time that part of the function is just containing x only, or the part you're differentiating with respect to, then it's the standard derivative. Anytime it has the other variable in it, you've got to go through that variable with a chain rule. Okay. Now, in practical terms, all that happens is y prime pops out of these things, right? So you don't have to make it too overcomplicated, right? It was the standard derivative, so 2y, and there's always attached a y prime to it. Wow, there it is, right? It's a very low-level way of looking at it, but it tends to work almost every time. You know what I mean? Okay, now we've got to solve for y prime. We're trying to find dy dx. That's what this symbol is here, right? That's dy dx for us. So I'm going to write it like that, because in other problems, it could be dy dt. It could be other letters going on. So I'm going to write dy dx. Even though it makes it a little more cumbersome to maneuver around in the problem, y prime is much slicker in terms of just writing. But to keep track of what variables we're using, I'm going to write the dy dx notation. All right, we need to solve for dy dx now. It exists inside an equation. So I should just subtract 2x and divide by 2y. Agreed? Seems reasonable. All right, so dy dx is negative 2x over 2y. 2's cancel. So we get negative x on y. And this is quite common with implicit differentiation problems, that you get both variables in your result. Okay?
Wait, what did you just do?
I subtracted 2x and divided by 2y. And that solves for the derivative we were looking for. Because the derivative can now pop up anywhere inside the equation. Or 2 times or 3 times in the equation sometimes.
Okay, so how do you go from 2x plus 2y to negative 2x?
Sorry, I just did this. Like that.
Oh,
I
okay.
thought dy dx is an operation, not a
No, d dx is an operation.
dy.
dy dx is that operation done to y, which
So
should be a
Y
number.
prime.
Which should be a number.
It's what?
It's y prime. What's that? It's the slope. We now know the slope of the circle anywhere on the circle. We didn't have to break it into pieces. This describes it for every location on the circle. All right? And you see it matches up.